is it open?
Yes, it's fully open. Of course, there are some restrictions on the class size.
Okay.
I think 50 is the limit for physical classes, but otherwise, students are more or less back. How about yourself?
Yeah, we started, but students, not at all. It's all going online.
Oh, I see.
Yeah,
So
but we
this
are back to the campus.
right. So this conference is entirely virtual, or is there a physical location somewhere?
No, it's completely virtual. Completely virtual. Yeah. Yeah.
Right.
So George is telling that it's already, it's now live. So we can
Okay.
get started. Yeah.
Yep.
So may I request Dr. Arun to take over and introduce the speaker for today, Dr. Andrew.
Good morning, Professor Dr. Andrew. So it's an immense pleasure for us to invite.
I lost your sound.
Is it audible?
Yes.
Yeah. So a small introduction about your profile. So Professor Andrew V is the class of 62nd Chair Professor of Physics and former Vice President of University and Global Relations at the
Sorry, we lost your sound again.
Just a minute, Dr.
Hello.
Yes, good.
Is that audible?
Yes, it's audible. I think there was a loose connection.
Okay. So the Professor V, who was a Dean of NUS Facility of Science from April 2007 to March 2014, is the past president of Singapore National Academy of Science. He is also the director of the Surface Science Laboratory in the Department of Physics at the NUS Faculty of Science and an adjunct scientist at the Agency of Science, Technology and Research Institute of Material Research and Engineering. Professor V was awarded the President's Medal in 2008 by the Institute of Physics, Singapore, as well as the UK-Singapore Partners in Science Collaboration Award in 2006 as a visiting scientist to Imperial College. Professor V's research interests are in surface and nanoscale science, scanning, tunneling microscopy, and synchrotron radiation studies of the molecule-substrate interface, graphene and related nanomaterials. A fellow of the Institute of Physics, UK, the Singapore National Academy of Science, and as well as the Institute of Physics, Singapore, he has published more than 400 internationally referred scientific papers. He is an associate editor of the journal ACS Nano since 2011 and serves or has served on several journals' editorial boards, including the Applied Physics Letter, Journal of Applied Physics 2009 to 2011, and Surface and Interface Analysis, and Surface Review and Letters. He holds a Bachelor of Arts honors in physics as well as a master's degree from the University of Cambridge. He received his DPhil from the University of Oxford. So his major area is ferromagnetic 2D materials. Once again, we are happy to invite you for this presentation, sir. So you can start your presentation.
Okay. Thank you, Chairman. Thank you, Dr. Arun, for the kind introduction. And thank you, Dr. Namula Grace, for this kind invitation. And I also know just now another of your speakers, Reddy, was on, and he was a former colleague. So hello to him if he's online. So greetings everyone from Singapore. I think it's nice that we can continue to have virtual conferences even though the pandemic is still on. And I think, I'm not sure how many of you are listening, but I gather about 100 or so participants in this conference. And I think most of you are from India, and I guess during normal times, many of you won't have the opportunity to attend such international conferences. So thanks, Dr. Namula Grace, for organizing this. And I've noticed you have an excellent slate of international speakers. So today, I'm going to talk about ferromagnetic materials. As you heard from my introduction, our group is a Surface and Interface Science group. And we've been working on 2D materials for the past decade, initially on graphene and then on transition metal dichalcogenides and other materials. And what I'm going to talk about today is really our work from about 2017 onwards, just the last few years, round about the time that this field began. So I shall focus now on 2D materials. And the picture you can see there is a picture of NUS University Town for those of you who have visited. And this is another picture. And NUS, you might know, is Singapore's flagship university. And of course, you're welcome to visit. I hope some of you have a chance to study there too. So before I begin, I'll just give a very brief introduction of our lab and the facilities we use. Let me first introduce two centers on NUS that we are part of. One is the Singapore Synchrotron Light Source. It's a facility, it's a common facility that we use. And I, in fact, set up a beam line in around the year 2003, about 20 years ago. And this is the surface interface and nanostructure science beamline. So the end station basically has a lot of surface analysis tools, and it's a soft X-ray beamline. Now, another center that our students and postdocs use is the Center for Advanced 2D Materials, which was set up around 2010 or 2008, I think. Essentially with the emphasis on growing and making devices out of various kinds of 2D materials, starting from graphene in the early days, now to other kinds of 2D materials. And some of our students use these facilities if we want to make devices out of our 2D materials. And the next slide shows our specific lab. So being a surface science lab, we have mainly systems in ultra high vacuum. So we have an ultra high vacuum environment because we want the surfaces and interfaces to be very clean. So we don't have stray atoms or molecules lying on the surface when we do experiments. And also because some of our techniques require such an environment. So today, the results I'm going to show are largely from our low-T STM and low-T STM AFM instruments. And we grow our 2D ferromagnetic materials using this system, which now has been upgraded. So we joined the MBE system to this RPAS system. And also shown is the original system over 30 years that we installed in our lab. This was the first VGS lab in our lab and in Singapore. And this is a physical photograph of my research group. Of course, our last physical meal was in Christmas 2019. As you know, last year it was impossible for us to have any physical get-together. So this was an important occasion, and I hope that this Christmas we'll be able to have a meal together again. So the scope of my talk, I'm going to give you a general introduction to 2D materials because I assume that some of the audience may not be so familiar with this topic. And then I'll focus on some of our key works in this area, and all the works were published in the last 3 years or so, because this is really our latest area of research. So I'll first talk about our work with vanadium dichalcogenide 2D materials. And then finally, I will end with our latest work on chromium tellurides. So I will give a broad overview of all the work in our field, and I won't go into too much of the detail. If you're interested, you can read the papers or you can email me with any questions. So the field of 2D materials. How will it impact the future? So when we think of flexible electronic devices of the future, we think of materials beyond silicon. And 2D materials are ideal in a sense for these because, of course, being monolayer thick, they are flexible. And they cover a whole range of materials that can be used for electronic devices. So you can see here a picture of transition metal dichalcogenide materials and a picture of graphene below. So transition metal dichalcogenides have become interesting for the past few years because although graphene is a fantastic material, it is a semi-metal. It does not have a band gap. So you can't really make transistors out of it because you can't switch it off. So transition metal dichalcogenides, they have strong spin-orbit coupling, fairly optical selection rules. They can display quantum spin Hall effects. So essentially, they can range anywhere from insulators to metals to semiconductors to magnets to superconductors, because we have a whole range of transition metals and chalcogens to choose from to make them. So you can see the field 2D magnets has obvious applications in non-volatile storage, spin filtering, spin injection, and detection. And of course, they can be combined with other 2D materials like graphene, which also has long spin diffusion lengths and very suitable for spintronic devices. Now, we wrote a review in Infomet in 2019. Zhang Wen, who was my postdoc then, but now she's a professor at Northwest Polytechnic University in China, was the main author. So this figure summarizes the field. So the field of 2D magnets really is a combination of two existing fields, that of spintronics and that of 2D materials. So we're bringing spintronics to the 2D field. And 2D magnets, or 2D van der Waals magnets, because these 2D films are normally have van der Waals interactions between other layers. They can be extrinsic, so the magnetism could be introduced by defects, dopants, functionalization, and so on. Or they could be intrinsic, so intrinsic to the compound used, it's magnetic. And of course, we can make many devices out of them. In terms of growth, of course, we can use the many growth methods that have been talked about, like the previous speakers talked about, but we're going to focus on MBE here because it is a very controllable method and we can grow high quality 2D magnetic materials. Now, of course, there are challenges and opportunities in the field that keep the field going very strong. So it's quite a hot topic right now. One challenge, of course, is scalability. To make devices, you need to make large areas. You need the materials to be stable in the air. You need high Curie temperature. Curie temperature is a temperature above which the material becomes magnetic, okay? Before that, below which it is not. So ideally, we want the Curie temperature to be above room temperature so that our devices can work at room temperature and do not require us to cool them down. And of course, there are many interesting physics phenomena at magnetic interfaces, and I list them here. I won't read them out, that make this field very interesting in the basic sciences as well as in potential applications. So my colleague, actually, Novoslov is now my colleague in NUS at MSc department. You recognize that he won a Nobel Prize in 2010 for graphene. So they wrote a review for 2D magnetic materials. Essentially, I just give this to you so that you understand the basic physics. So in a 3D system, you always see a magnetic phase transition. You always see a finite cubic temperature. But in the 1D case, the long range order is only possible at t equals 0. So that's the limitation of the dimensionality of the material. Now, 2D is somewhere in between. 2D materials can have a finite Curie temperature, but it depends on the spin dimensionality n, which I'll explain in the next slide. So this explains the spin dimensionality. So in the case, the Mermin-Wagner-Hohenberg theorem states that thermal fluctuations destroy long-range order in 2D systems at any finite temperature when the spin dimensionality is 3. So in this diagram, you can see when the dimensionality is 3, the spin can point in any direction in free space, and you will not get any transition temperature. This empty graph is flat because of thermal fluctuations. But when n is 1, the opposite extreme where the spin can only be up or down, you have what is known as the Ising model. In this case, because of the intrinsic anisotropy of this 1D system, this opens up a gap in what is known as the spin wave spectrum, which suppresses the effect of thermal fluctuations. So in this case, it is possible to get a transition temperature, Curie temperature here. And in the intermediate case for the planar or 2D magnets, what is known as XY model, you can get a quasi long-range order due to the theorem that due to the physics that was discovered by the recent Nobel laureates Berezinski, Koselleck, and Taulas, right? So they proposed this temperature, this Kosterlitz-Taulas temperature, TKT over here, where you can see some quasi magnetic order and some transition at this case because of the topological properties of the 2D planar magnets. So, okay, this is my last slide on the physics of it. So essentially, you can describe this 2D magnets using the Heisenberg spin Hamiltonian as shown. And you can see this is Hamiltonian, and J is the exchange coupling between spins S1 and Si and Sj, right? This is the spin exchange coupling term you always see in quantum mechanics. But in addition, there's A and lambda. These are on-site. A is on-site, and lambda is intersite magnetic anisotropies. So if you have some anisotropies, these terms come in, right? And you will see that in the case of isotropic case where n equals 3, this A and lambda is 0, right? But for the Ising or the XY model, these are non-zero. A can be some finite value, and hence this explains the properties of the material. So if you can introduce some anisotropy in your material, then these terms are non-zero, and then you can get 2D magnetism, right? So this is an early review in Science where it summarizes the 2D magnets that have been discovered up to then. So here, again, the Mermin-Wagner theorem says that 2D materials that are isotropic cannot be magnetic, but you can introduce some anisotropy. So one would think that only extrinsic 2D magnets appear, but in fact, there are some intrinsic 2D magnets. And because they have some small uniaxial magnetic anisotropy within the system. And the ones that have been discovered are those highlighted in blue, like the chromium halides here, as well as CGT and FGT, these alloy systems. And today I'll talk about the vanadium diselenide systems. Of course, this library is due to, I believe, what people predict ferromagnetic, antiferromagnetic 2D materials will be. And of course, there's still a lot of work needed to discover these new materials. So let me give one example. One of the early intrinsic 2D ferromagnetics magnets studied was chromium triiodide, right? And this is work from Washington that basically demonstrates that you can get 2D magnetism in bilayer chromium iodide, and you can control the magnetism by electrical means. You see this gating here. And electrical means are important. It means you can make a device that you can control with voltages. So hence, that's the importance of this work and importance of and the potential applications that this material can have. So let me go on to our first material, 2D vanadium diselenide. So let's look at the transition metal, transition row of metals in the periodic table. You see all these elements that you're familiar with, and you can expect many of them to be magnetic from the electron configuration because you see unpaired spins. So the question we want to ask is, can we make TMD compounds magnetic in the 2D limit? And the question certainly is yes. And work has been done on manganese and vanadium, as I'll show in a while. And so this work in 2018 by the Irvine group, Kawakami's group, showed that manganese selenide 2D films are ferromagnetic, but you can see the ferromagnetism is quite small, the hysteresis, and of course they use standard magnetism measurements to measure them, and I'll comment on that. And another paper in Nature Nanotechnology in 2018 by the Florida group, University of South Florida, Batzel group, showed that vanadium diselenide monolayers showed strong room temperature ferromagnetism. That's why this work attracted a lot of attention, because it's room temperature. And that has, of course, as I mentioned earlier, a lot of applications. So you see the data, raw data here showing the hysteresis and so on. But let me just highlight here some key points of this paper. So before this paper is published, theoretically, theorists have calculated the magnetic moment in 2D vanadium diselenide, and it arises mainly from the vanadium ions, as we would expect, and it has a value of 0.6. It's about 0.6 magneton, right, per ion, which is much smaller than that of the traditional 3D ferromagnets like iron or cobalt. But their paper actually reported a huge value, an order of magnitude larger. So this raises some questions. Either the theory is wrong, or something in the experiment in the explanation is not quite right. So in our view, we think that using bulk magnetic tools like squid and so on to measure 2D magnets has a problem, just like in the field of dilute magnetic semiconductors in the past, where it is very difficult to extract weak magnetic signals, and very often some extrinsic effects like magnetic dopants or impurities might be introduced into the system, whereby you measure these effects. So in our view, and we were working on this material at the same time as well. So we wondered about these results. So we actually did these experiments about the same time. But this time we used a technique known as X-ray XMCD, X-ray magnetic dichroism. And basically you get the spin information from the material, but it is element specific. So here you see STM images of this vanadium diselenide that we grew, and it's metallic in a 1T structure. It has a small band gap, a very small one. And what is more important, when we use the circularly polarized X-rays, and then take the difference between the left and right circularly polarized X-ray from the X-ray absorption age of vanadium, we can get what is known as the circular dichroism magnetic signal from vanadium. And you can see that taking the different spectrum, the percent of signal is extremely small. Okay, it's 0.1 or so, and which in effect is around the noise level. So we had a lot of difficulty measuring any magnetism in our MBE grown vanadium diselenide. And here are additional measurements using squid and so on, which I won't go into. Just to mention that all these other measurements we used showed that there was no sign of magnetism in these materials. And we postulated in this paper that we have a frustrated, that's why the paper is called evidence of spin frustration. You can see in this structure here, where if you have up and down spin as shown here, the spin of this in this part of the lattice would be frustrated. It could be either up or down. So we concluded that vanadium diselenide is a frustrated magnet. It's trying to be magnetic, but it is not. It needs some extrinsic perturbation in order to make it magnetic. And we think that is the reason for the magnetism reported in some previous work. So This is some RPS results on the electronic structure that showed small CDW gap opening when cooling. Right, so that was our conclusion, that vanadium diselenide is a frustrated magnet. And we confirmed that by when we put some magnetic element like cobalt on this vanadium diselenide, then we see an XMCD signal from vanadium as well as the cobalt. And the interesting thing is that the dichroism is in opposite directions. So these are the results. This is a XMCD results. This is the STM. You can see the cobalt is clustered. It's not a very uniform film, but nevertheless, it's about 3 monolayers. And here you can see the data, the indication of ferromagnetism. And we noticed that it's antiferromagnetically coupled between cobalt and vanadium diselenide. That's why these hysteresis curves are opposite way around. So the cobalt is this way and the vanadium is the other way, right? And we can see the hysteresis in this case. So yes, now I've mentioned all that. So this paper in ACS Nano in 2019 essentially confirms that we can make vanadium diselenide 2D vanadium diselenide magnetic if we antiferromagnetically couple it with some magnetic material, in this case, cobalt, right? And we have further evidence that intrinsically is not magnetic when we studied the other vanadium dichalcogens like vanadium ditelluride. So we did the same thing. This is monolayer vanadium ditelluride. And again, in the XMC signal, you can see the difference between the left and right polarized, left circularly and right circularly polarized light. The difference is almost zero. So again, we can see no evidence for intrinsic magnetism in this vanadium ditelluride. And the interesting thing is that the same group that published at Nature Nanotechnology from Florida, Betzel group, also worked on vanadium ditelluride. And the interesting thing is this time they did XMCD. And again, they confirmed there's no dichroic signal. So they also found that this material is not intrinsically magnetic, which casts doubt on their earlier result on vanadium diselenide. And so this was in agreement with our data. But nevertheless, they also showed you can make other 2D non-magnetic TMDs like molybdenum ditelluride magnetic by incorporating, for example, vanadium impurities, because vanadium introduces magnetism. So they showed that in this case it's magnetic. So that confirms our postulate. Now, later that year, a colleague in our chemistry department, KP Low, published this paper in Advanced Materials showing that chemically exfoliated vanadium Se2 monolayers have room temperature magnetism. Now, of course, this initially worried us because here we say that it's not intrinsically magnetic, and then they published a paper that showed room temperature magnetism as well. But we just take note that, okay, this is the magnetism. This is the measurements, magnetic measurements. And the interesting thing that is that after annealing, when you have pristine, the magnetism seems very small. But after annealing, you can see a larger hysteresis here. And when they did computations, they found that if the vanadium selenide was intrinsic before annealing, the magnetism is lower. But when you anneal it and it becomes selenium deficient, so VSE 1.75 here, it becomes more magnetic, consistent with this experiment. And if you saturate the vacant selenium vacancies with thiols or oxygen, the magnetism drops. So this suggests that the defects seem to play a role in the magnetism. And the fact that they observed some magnetism in the intrinsic vanadium diselenide could be due to the fact that they did the whole experiment by chemical means. It means that the sample were exposed to chemicals, exposed to air, and inevitably some external adsorbates or impurities may cause this magnetic signal. So their results, we postulated that selenium vacancies could cause the ferromagnetism observed. So we wanted to do this work carefully in our STM using MPE grown. So our PhD student, Rebecca, who's just submitted a thesis, basically asked the question, can selenium deficient line defects in monolayer vanadium diselenide induce magnetism, right? So she deliberately heated the sample to cause these increase in the line defects that you see. And these are STM images of the line defects, which we can see are due to selenium deficiencies. And we have worked out the detailed atomic structure of these line defects that have a missing row of selenium, right? And then with both the intrinsic and the selenium deficient sample, she did MFM measurements, which are shown here, as well as XMCD measurements, which are shown above. And you can see that in the XMCD, pristine vanadium diselenide, as we had shown before, is not magnetic. But defective vanadium diselenide, you can see a larger dichroic signal here. Similarly for MFM, on top is intrinsic and the bottom is defective, and you can see an increase in this green color regions, indicating that defects of some sort seem to be inducing localized magnetism in the images. And here are the data of the phase changes that in these two sets of images. So we have shown that defects, and of course we have done calculations that show that before the reconstruction, after the reconstruction, you can see a net increase in magnetism. So our conclusions are that silicon deficient line defects can cause ferromagnetism in pristine vanadium diselenide, and DFT calculations confirm this. And we hypothesized that some of the papers published prior to this that showed magnetism could be due to defects in the materials. So our current understanding of magnetism in vanadium dichalcogenides are that if we can grow very high quality vanadium diselenide, for example, with MBE, then we show no intrinsic magnetism, in spite of the fact that certain authors did report some magnetism. And we explain and we support this by the fact that even in vanadium ditelluride, we and other groups did not observe magnetism. But nevertheless, we can make these vanadium dichalcogens magnetic by either absorbing magnetic atom element on it by proximity effects, so we can induce some magnetism, or we can induce defects. If the defects are selenium deficient, they can induce magnetism, and it basically these things cause magnetic anisotropy, which lifts the large magnon excitation gap that I mentioned earlier, and it lifts the restrictions imposed by the Mermin-Wagner theorem. Right. So that was our study, which took most of 2019 and 2020, our publications. Now, in the last 5 minutes, I just want to mention our latest work, which is submitted, is still under review. This time we worked on chromium ditelluride. Okay, and this work also done by Rebecca, is submitted now. And of course, coming back to this periodic table transition metal row, we would expect spin to be introduced in any chromium 2D dichalcogenide compound, right? So this is some prior work on chromium selenide nanosheets done by this UCLA group, and they showed ferromagnetism. And in fact, they specifically studied chromium diselenide on tungsten diselenide heterostructures. And the main results is that charge transfer between this tungsten diselenide and as well as interlayer coupling with this chromium diselenide play a critical role in the magnetic order. So while they show that chromium, these chromium selenide 2D compounds are magnetic, the interface plays an important role. And these are some of the results where they showed layer dependence magnetism, and they mapped out the phase transition space of the material. So it's an interesting material that has potential applications. Here's another paper specifically on chromium TRT2, which is the same material that we have grown, and a paper just published. And this time they showed that the 2D chromium ditelluride is air stable, right? And it's metallic. And they did measurements of the anomalous Hall effect to show magnetism. So they used electro method to show the magnetism. And they also showed that there is an increase in Curie temperature as the thickness decreases from 130 nanometers to 7.6 nanometers. So they didn't really reach monolayer. Well, it's near monolayer, but it's not monolayer. It's few layers, 7.6 nanometers. And here are some of the key results. And I'll just want to highlight the fact, the Curie temperature. So you can see on the left here, it's 7.6 nanometers. So the Curie temperature is about 100 and just below 200 degrees Kelvin. Whereas in a thick film, you can see the Curie temperature is a bit lower. So as they move towards monolayer, the Curie temperature gets higher, but it's not room temperature yet. So we submitted this paper, which is on arXiv. So if you're interested to look, you can look at this link. We hope it will be published soon. And this time we studied the monolayer as well as the few layer chromium telluride in detail. We found that the few layer forms mainly the CR3TE4 stoichiometry. And when we thin it down to a monolayer, you actually have vacancies in this row of tellurium. And in fact, from XPS, which I'll show later, the ratio is more 1:2. So in effect, the monolayer is more like chromium ditelluride, right? So this is our postulated structure based on the data, which I'll show you. This is the STM data showing growth at different temperatures, and even at 100 degrees centigrade, which is a very low growth temperature and certainly compatible with silicon CMOS technology, you can see we can grow this monolayer chromium telluride film. You can see this is the step height. That's about one monolayer, okay, 0.9 nanometers. And here is the XPS. I'll focus on the XPS, which shows the monolayer and the bulk. So from the XPS, we can get the stoichiometry. The thicker film has a ratio of 3:4 chromium to telluride, and the monolayer is more 1:2, which is why we proposed the structure we saw 2 slides ago. And the more important thing is the magnetic measurements show that for the monolayer, here comparing the monolayer and the thicker film using SMCD again, you can see in the monolayer film up to around just above room temperature, there's still some dichroic signal, whereas the thicker films, it disappears below room temperature. So we plot the Curie temperature. You can see that for the thicker film, the transition occurs about 200 and something Kelvin. And for monolayer, transition is above room temperature. And hence, we think this result is important because when you think about magnetism, magnetic applications in devices, storage devices, you really want them to work at room temperature. So, and we explained it. This is some calculations that was done by a collaborator. And the blue and the red show charge transfer that occur at this interface. We grew it on graphene, right? We grew it on graphite, but the simulation was graphene, which approximates one layer of graphite. And our main conclusion was that by doing a better analysis, there's about a transfer of about 0.1 electron per atom from graphene to monolayer CR3T4, which we attribute to be some of the causes for this higher Curie temperature. So, right. So I'll conclude here with my final remarks on the future perspectives. As you can see, this review in nanoscale shows all the different kinds of applications. If you have 2D magnets, you can make 2D spin filters, you can make tunnel barriers, spin orbit Hawk devices, and so on, spin transistors. And moving forward in the age of quantum information science, there is a role for 2D materials. And here's a review by Mark Hersam's group, my co-associate editor in ACS Nano. And he shows all the various applications you can use for the quantum computing space using 2D materials. So I shall end here with acknowledgements as usual. And I want to acknowledge in particular the people in red who did the work, Rebecca and Chu Rui, who are our PhD students, Chang Lei and Yu Li, who are my postdocs, and Johnny Wong and Zhang Wen, who were my postdocs, but now are professors in NWPU, and of course, external collaborators, as well as our funding support from all our funding agencies. So thank you for your attention, and I'll be happy to answer any questions.
Professor, thank you for your wonderful talk. So we have a few questions. So the first question is there any, like, why was the CO chosen specifically?
Oh, okay, that's a very good question. So the question is, why do we choose CO? Well, because CO, you know, cobalt, iron, nickel have the strongest magnetism, and hence we wanted to start with a strong ferromagnetic element to induce magnetism. Okay, you're referring to this work of interface hybridization with CO. Now, of course, we could work with iron, nickel, and other magnetic compounds, and we will do that. In fact, we are undergoing a research program where we're trying to study interfaces of different 2D materials, so 2D heterostructures, whereby one of them is magnetic, and see whether we can get proximity magnetism in the other material. And we're also doing it with molecules, since some of our other research fields are in magnetic molecules. So the answer is yes, we can use many other materials, and we only chose cobalt because it is a common material that is ferromagnetic.
Okay, thank you. The next question is, the chromium increase in the monolayer is also shows some specific changes, whether
the chromium, I suppose this is referring to the last work, the chromium increase in the monolayer. Yeah, okay. Now, I did mention to you that from XPS, the stoichiometry actually does change, and we are suggesting that the stoichiometry, the ratio changes from 3:4 to 1:2 here. So in a sense, the chromium does increase, but actually it's because the tellurium decreases. So in the formation of the monolayer, it forms by annealing it to higher temperature. And with annealing, tellurium being the more volatile element would preferentially dissolve. So this is our reason for why we believe that the chromium increases. I hope I answered your question.
So if no questions, I would like to thank you very much, sir.
Mic is muted. That we have one last question. So during the chemical exfoliation, is there any increase in the temperature, Professor?
Okay, the chemical exfoliation experiment was not done by us. As I mentioned to you, was done by our colleague in the chemistry department, KP Low. So I do not know whether there was any increase in temperature. There could have been, but the key point is that when you do chemical exfoliation, you cannot avoid introducing some external elements into your sample, and hence we think that that the magnetism measured is extrinsic, right? So, but if you want to know details, please look at this advanced materials paper.
Okay, Professor, one last question.
Sure.
Okay, this vanadium disulfide will be well ordered to get magnetism. Is it permanent or instant magnet?
Okay, vanadium disulfide. Now you're asking the other we haven't worked on vanadium disulfide. We worked on vanadium diselenide. So what was the question again?
Vanadium diselenide will be
selenide.
well ordered to get magnetism. Is it permanent or instant?
Now, as you can see from our work, we showed that a perfect vanadium diselenide film is a frustrated magnet. That means in our view, it is not magnetic. But to make it magnetic, then we have to introduce an isotropy, which in our case was introducing defects, which I showed here. By introducing defects, we measure magnetic signals. And hence, to answer your question, if it's perfect, there will be no magnetism, just for this case of vanadium diselenide.
Okay. Thank you, Professor. So,
my pleasure.
We'd like to thank you for joining our conference. So,
thank you for listening.
Thank you.
Sir, once again, thank you very much, Professor Andrew, for your nice presentation. In fact, really,
hi, ready?
Yeah, very interesting, sir. Very interesting, and thanks for your initiation, all your nanoscience and initiative for the last 20 years. I think it has grown a lot, and then keep continue, sir. Thank you very much, sir. Okay.
Yeah, nice to see you.
Okay, thank you.
Yeah.
Thank you once again, Dr. Andrew, for a nice presentation, and thanks for joining. Thank you very much. Dr. Abdul and Dr. Krishnan, I think Dr. Abdul has joined.
Yeah, can you hear me?
Yes. Dr. Abdul, can we, can we log off from the link and just rejoin in the same link?
Sure, sure.
Yeah. Krishnan sir, you can join the same link.
Hello, can you hear me?
Yes, Krishnan sir, we'll join the same link. You can just leave the link and rejoin so that other participants can join.
Okay, all right. Okay,
Yes,
I'll do that. Thank you.